Okay, today is Thursday, February 13th, and we are one nice delay. So we were ready for investigation 3. And what we're going to do when you come in investigation 3, you've already run your cart down, pointed in first. That's option B, so you'll be able to pick your winner and fill that out. And then we'll turn it around, run it flat in first. And whichever that winner is, you'll run it that way for the rest of the testing. And then we'll put a tail on it, wings on it, tail and wings on it, and try some of your ideas. But let's come back to that. What we're going to do is jump on ahead to the next thing, which is looking at what's adding weight to your cart going to do. And that's investigation 4. Gravity is the source of the force and the energy that is making that cart roll down the ramp and then continue across the floor because it already got fast and had some momentum. Now, Galileo used the ramp to study the acceleration of gravity. So this is how we get our information. Let me see. I don't imagine this is Galileo's actual ramp. This is probably a model built on his plans. But a ball would be let roll down this ramp and it would ding a bell, ding a bell, ding a bell, ding a bell, and you'd have those bells spaced out so the time interval ding, 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 ding was the same like music would be, because at that time they didn't have stopwatches. And it found out as it rolled down, the ball rolled down the ramp, that it's not going very fast at far, so the bells are pretty close together. But the faster the ball goes down the ramp, the more spread out the bells get. And that's how he was able to study motion and velocity and ultimately figure out what acceleration was, because nobody else had figured it out up to that point. Okay, so let's continue. So remember, weight is a force, and it's mass times acceleration. And the net force is, if there's a bunch of forces added together and some of them cancel, there's going to be a leftover maybe. And that leftover, that net force, when you add them all up, is what causes the acceleration. And so if you divide, your book likes to do it this way, if you divide the mass over here, you end up with force divided by mass is acceleration. That's fine. This is the same as F equals ma. So let me ask you a question. I want you to think about this for 20 seconds. Add mass to the cart. What's your cart going to do? Is it going to go farther? Is it going to go shorter? Is it going to go the same distance? What should happen? You probably have an opinion about that. You've probably formed a conclusion about that. But let's do it the scientific way. Let's do the conclusion last. Or at least let's look at it in theory. Let's do both of those things. Most people are going to form an opinion based on what they think, and then, oh, that must be what's true. That's kind of the way we're today programmed to think, but that's not a scientific way to think. You got to look at the evidence. Now remember, Galileo said, based on rolling these evident things down the ramp, hey, all objects are going to fall at the same rate in a vacuum. So I asked you to think about this for 20 seconds. What ought to happen is adding the weight shouldn't matter. Because if you add weight, you should have more friction, you should end up where you are. However, there's a problem. This system involves friction, multiple sources of friction, and friction makes things act goofy. For example, just having things fall in the same rate in a vacuum. You drop a hammer and a feather here on Earth, there's air resistance. Air resistance is friction. That makes it not behave the way it's supposed to behave. Well, let me back up here one more time, because I didn't say something real important. What should happen if you add weight to your cart let's say you double its mass, or you 10 times its mass by adding weight. If the mass went up by 10, but the weight would have went up by 10. And if you have 10 times the amount on the top and 10 times the amount on the bottom, you should end up with the same acceleration if you add weight to your cart. It shouldn't make it perform better or worse. Now, that being said, again, there's a lot of friction involved in these. And when you put friction in it, things act wonky like they're not supposed to. So what should happen in theory is the acceleration should stay the same and the weight shouldn't matter. But you will see some effects because it's a complicated system. Now let's go on. Using Newton's laws. So what happens in a crash? Newton's first law of motion can explain what happens in a crash. You're going 20 miles an hour, car hits a tree stump, stops. What are you doing? Well, you're still going 20 miles an hour. And if you don't have a seatbelt on and you don't have airbags and all that, you're going to hit the dashboard and the steering column and the windshield going 20 miles an hour. That's going to be a huge problem, potentially lethal problem. Why do you keep moving? Because you have inertia. Once you are going, your tendency is to keep going. And it takes something to slow you down and stop you, like friction. So safety belts and airbags, what that'll do is it'll help you slow down with a negative acceleration or a deceleration so that you don't slam into the window and dashboard and that. Because if you hit the car parts like that, you're gonna come to a stop in this much distance. And to change your velocity from even 20 miles an hour to 0 in this much space, it's going to do a lot of damage. If you can do that 20 mile an hour deceleration over a few feet or more, a meter or more, it's going to be high, but survivable. So this lowers that acceleration, that negative acceleration, that deceleration, to have you strapped to the car where you're going to, the car is going to crumple up and it's going to come to a stop in several feet maybe, as opposed to a couple of inches. So Newton's second law in gravitational acceleration is F equals ma. And if it's gravity, that's g, and there'll be a g there. Maybe. So this equation also becomes force of gravity on an object, which is its weight, equals mass times the acceleration of gravity, which is 9.8 or 9.81 meter per second squared, and we can use 10 because that's close enough. So the metric unit for acceleration and gravity, because gravity is an acceleration, I'm going to argue, so does Einstein, meters per second squared. So avoid force of gravity unless you follow up on an object which is its weight. So air resistance is next, and this is a problem with your car that we should be testing in streamlining. We're going to do streamlining today. So your cart's coming down the ramp, it's going across, and you got it moving faster because you lowered the friction in the axles, and you've got it going farther. And now it's going fast enough that it's got to push through air, and that's making a difference. So we want to make that air resistance less. We want to put wings on it and see if it can slice through the air better. We want to put a tail on it and see if it can slice through the wind better. We want to put both on it and see if we can slice through the wind better. We want to do changes to your idea, see if you can make it slice through the air better. So gravitational acceleration causes objects to fall. Air resistance is a fluid friction that opposes the object falling through air. It acts opposite to the direction. So if I have this and this, and I drop them, this eraser isn't going to be affected by much air resistance because I'm going to drop it this way, and it's got a little more mass than this ping pong ball does. And let's see if we can see any difference here. Maybe not, because they're not going fast enough. Yeah, you can't see that difference there. But if I have a piece of paper and eraser. We could probably see a difference. This doesn't have much mass, this has more mass, but this doesn't have hardly any air resistance, and this will. Ah, there, you see a big difference that time. In a vacuum, on the moon, they'd fall together, but the air's in the way. So the amount of air resistance depends on the size of the object, it depends on the shape of the object, it depends on the speed of the object, because the faster it's going to go, the more air resistance it has. And it also depends on the properties of the air. I was talking about this when we did the egg drop at University of Toledo. This steel container for my egg drop, dropped it, accelerated all the way to the ground over 100 and, I forget how many feet that was, that fell, 160 feet maybe. Left a crater in the ground, but the egg was fine inside because of the way I designed it. Everybody else's container was real light and fluffy and just tumbled down and plopped into the ground going 10 miles an hour. This was going accelerating all the way to the ground. So we may do egg drop later in the year, and you'll have to toy with air resistance. Okay, air resistance is the reason that feathers, confetti, leaves, that piece of paper, all fall more slowly than pennies fall or stones fall. Without air resistance, all objects would fall with the same acceleration on Earth of about 9.81 meters per second squared. A dust bunny, even a balloon, even a helium balloon, even a weight in a vacuum where there's no air, fall together because there's no air to buoy that up. Whoops. Okay. Next. Okay, so the amount of air resistance increases as the speed goes up. You may have noticed that. Put your hand out the window of a car. You're going 15 miles an hour, not much wind. You get going 60 miles an hour, a lot more air resistance on the same hand. Eventually, if you're falling, even if you're this guy, eventually if you're falling like Felix did, far enough, fast enough, you won't be able to go any faster. You're going to hit a terminal velocity because the air's in the way. So eventually the upward force of air resistance is going to balance your gravity, your force of gravity on you, which is your weight. And that force is going to become equal to your weight. And then you're going to just fall at the same rate. So the net force would become zero because you're no longer going faster, you're no longer accelerating. The acceleration becomes zero. And you would hit what's called terminal velocity. So if you jump out of an airplane 2 miles up, 3 miles up with a parachute on, hopefully, and you hit that wind and you start slowing down because you're hitting air, your forward motion, and start falling straight down eventually, you're going to speed up going down for a little bit, but after 5-10 seconds, you start to approach terminal velocity. You're just not going to go any faster. You're going to go about 120 miles an hour, and that's about as fast as you're going to go. Okay, so that's free fall. If an object's falling and there's no air resistance, and like on the moon, there's no air resistance because there's no air. There's a little bit of gravity, but there's no air. You would go faster and faster and faster and faster and faster and faster. You're in free fall if gravity is the only force acting on you. So objects that are in orbit, like satellites, you can see SpaceX satellites launched and they get in that line. Maybe you've seen those before. So you can see satellites when the conditions are just right. They are actually in free fall around the Earth. So here's a model I made of the Earth that's really bad. It's blue because it's supposedly water. These brown splotches are land masses. That's ice on one of the poles, maybe Antarctica. And let's look at what would happen. Okay, so let's look at what would happen on the next video. This is something that represents an object dropped, an object thrown out, and an object shot out. Think about it.